Let us now talk about acceleration due to gravity. This is commonly denoted by small letter g. Mind you, there is large difference between capital G and small g so long as this chapter is concerned. Capital G was used for universal gravitational constant whose value is constant for all the masses, all the planets. But so long as this acceleration due to gravity small g is concerned, its value is not constant, rather it is confined to one particular mass. For Earth the value will be something else, for the moon the value will be something else. Remember that small g is called acceleration due to gravity and capital G is called universal gravitational constant, and both of them are entirely different things. If you consider the Earth, then how will you calculate the acceleration due to gravity? Consider the Earth. Let us suppose this is our Earth, and let us suppose this is our location. Say any mass small m is kept on the surface of the Earth, and the distance between the center of the Earth and this mass is, say, capital R, and the mass of the Earth I am calling capital M. Remember that so long as Newton's law of gravitation is concerned, it was said that for spherical masses you can assume as if the entire mass is concentrated at its center. So maybe this Earth is shown as a large sphere, but you will understand right now that the entire mass of the Earth is concentrated at its center as it has been shown here. So there is a capital M like a point mass kept here, and there is another small m which is kept on the surface of the Earth as a point mass, and the separation between them is capital R. Capital R, you should understand, this is radius of the Earth. This is radius of the Earth. If you see the average value of this is approximately, you can say, 6400 kilometer, or in terms of meter if you write, this is 6400 into 10 to the power 3 meter. You understand? Now you see, this small m can be S or any object kept on the surface of the Earth. We have a particular weight. Let us suppose you are this small m. Then you have a weight which is acting in vertically downward direction. Vertically downward here means along this line, along this radius which is going to the center. This is the direction in which your weight is acting, our weight is acting. You understand? So now what is the concept of weight? You should understand that weight of an object, say mass m, weight of mass m is essentially the force with which this Earth is attracting this mass. You understand? What is our weight? Weight is the force with which this Earth is attracting us. So I am writing here weight of mass m is equal to force with which the Earth is attracting. You understand? The weight is just the force applied by the Earth on this small mass m. Now what is our weight? Weight is nothing but m into small g, that is acceleration due to gravity. And what is the magnitude of the force between capital M and small m? This is equal to as per Newton's law of gravitation, G capital M small m upon R square. You understand? What is this capital M here? Capital M is mass of the earth. Capital M is mass of the earth. Now if you cancel out these two small masses, then you get the expression for acceleration due to gravity, and that you can see this is equal to small g, this is equal to capital Gm by R square. So you can write this expression here, that this capital G, that is acceleration due to gravity, this is equal to capital G capital M upon R square. Now remember that we have derived this expression for the case of the earth. Let us suppose you are calculating the same thing for the moon. Then the value of capital G will remain constant, but this capital M will become the mass of the moon, and this capital R will become the radius of the moon. And for that matter, this acceleration due to gravity on the moon will change. You might be knowing that G on the surface of the earth is around 9.8 meter per second square, but when you go on the moon, then the value becomes almost 1/6. Why this change? Because this capital M and this is small r, that will be changing. And you see, just now I had said that capital G is a universal constant, but this small g is not a universal constant, rather it varies from place to place. And this is being called acceleration due to gravity, and this is being called the universal gravitational constant. Now, so long as the practical aspects of this small g is concerned, maybe here right now I have written it in terms of mass and radius. Sometimes you are expected to express this particular expression in terms of the density of the material. So how will you express this thing in terms of density of the material? Assume that the density of the earth is D. D is density of the earth. This earth is being treated as solid sphere. So if you want to express the total mass of this earth, capital M, then this is nothing but density into volume. Density into the volume of this earth. What is the volume of this earth? Volume is, for solid sphere, 4 pi by 3 into r cube. This is the total mass of the earth. Now, in this expression of acceleration due to gravity, which is Gm by r square, if you substitute for this capital M, you will get G into D (4 pi by 3 r cube) upon this r square. You understand? The acceleration due to gravity in terms of density you are trying to express, it will be something like this. And finally, if you are writing the expression of acceleration due to gravity small g, then this will become 4 pi by 3 G D R. You understand? So long as problem solving is concerned, you will find that frequently we will be using both these equations. Small g is equal to Gm by r square will be of use when mass and radius are given, and this expression will be of use when density and size is given. Sometimes in the question they will say that you have to compare acceleration due to gravity on two different planets. Sometimes the data will be given in terms of mass. Sometimes they can say the material of the planets are same. Material means the density. You understand? In case they are giving you data in terms of material of the planet, then you will have to use this expression. In that case, G will become proportional to R, but so long as mass is constant and only size is varying, then G will become proportional to 1 by R square. Now you see, this is acceleration due to gravity, which varies on different parts of the earth. It is not a quantity which is constant. If you go above the surface of the earth, which you call altitude, then also you will find that the acceleration due to gravity is decreasing. If you go below the surface of the earth, you will find that this acceleration is again decreasing. If you move on the surface of the earth, then also you will find that on poles the value is maximum. As you start moving down on the latitude, when you come to the equator, you will find that it has become minimum. Again, if you start going to the poles, you will find the acceleration due to gravity is increasing. You understand? So now we have to look how this acceleration due to gravity is varying with several factors. Mainly 3 factors we will be talking about. One is altitude, one is depth, and one is what is the effect of rotation and latitude of the earth. The normal value G is equal to 9.8, which you see, that is just on the surface, and that too an average value. You understand? But if you are moving up or going down or on different latitudes, then this value is not same, rather this changes. So let us talk about variation in acceleration due to gravity. Now let us talk about variation in acceleration due to gravity. As we said, there are mainly 3 factors. So first, talk about altitude. What is the meaning of altitude? Altitude means height above the surface of the earth. Understand? Altitude means height above the surface of the earth. You can denote it by small h if you feel like. Now consider again the earth. Right now, assume that you are on the surface of the earth and the acceleration due to gravity at this particular point is small g. As we had considered earlier that the entire mass of the earth can be assumed to be concentrated at the center. So you should understand that the capital M is concentrated at its center. This is the radius, say capital R. And now you have moved to some altitude. Altitude means this h is counted from the surface of the earth. Maybe several kilometers you have gone above, and say the acceleration due to gravity here is g dash. I am trying to say that whatever is the value on the surface of the earth, same value is not there at some altitude. If you consider the distance of this point where you are experiencing g dash, if you are denoting the distance from the center of the earth, you may call it small r. What I mean to say that this small r is the radius of the earth plus this altitude. You understand? R is the radius of the earth. R is radius of the earth and this small h you have, this is just the altitude. So the distance from the center of the earth to this point is smaller. Now you see, if you talk about the acceleration due to gravity at the surface of the earth, this is small g on the surface of the earth, this will be written as capital G M upon R square, right? Because the entire mass of the earth will be assumed to be concentrated at its center and on the surface of the earth. the distance will be simply capital R. But if you talk about the acceleration due to gravity at this point, that is g dash, then you will find it will be written as g m upon this entire distance, r plus h whole square. You understand? Or maybe in other words you can say g dash can be written as capital G m upon small r square. This is small r is the distance from the center of the earth. Now if you see the ratio of it, then you will find that you can write g dash upon g. If I am dividing these two expressions, this is equal to gm upon r plus h whole squared upon gm by r square. If you are taking the ratio of these two, you will find they can be expressed like this, and if you simplify, you can write it as r square upon r plus h whole square. You can understand that here, in general, acceleration due to gravity is proportional to 1 by r square. Understand? You are having this acceleration due to gravity decreasing parabolically as you are going above the surface of the earth. But let us suppose you have some special case of altitude is very small compared to the radius of the earth. Let's suppose you have a special case. Very small means 5 kilometer, 10 kilometer. Then using this expression may become difficult. In that case, if you simplify this thing and use some binomial approximation, you can very easily prove that g dash upon g becomes equal to 1 minus 2h by r. You understand? This becomes the special case when the altitude is very small compared to the radius of the earth. You understand? This is a general expression. Whatever you have written here, this is a general expression for any value of altitude. But in case altitude is small, then you should use this expression, in which you can say that this small g is the acceleration on the surface of the earth, and this g dash is at some altitude, small altitude h. You understand? This is the way it is varying, and you can see as you are going above the surface of the earth at a very fast rate, acceleration due to gravity is decreasing and decreasing parabolically. You understand? Now let us talk about the variation due to depth. Right now you were going above the surface of the earth. Now let us suppose you go below the surface of the earth. Then how this acceleration due to gravity is varying, let us discuss that. Now let us discuss the variation in g due to depth. Let us suppose we are denoting depth by small d. Now consider this is our earth and this is its radius r. At the surface of the earth, let us suppose the acceleration due to gravity is g, and you have gone at a depth d from this place. Depth d is a small d indicated here, and assume that the acceleration due to gravity at this point is g dash. As you had considered g dash above the surface of the earth, here we are considering g dash as the new value of acceleration due to gravity when you are at a depth small d. For that matter, in case you consider the depth of this point, from the center, then this will be indicated as small r. Small r all the time we are using as a distance from the center of the earth, O. And here you can understand that this small r is basically capital R minus d. Now see, the value of acceleration due to gravity g on the surface of the earth will be written as gm by r square, as you had done here. Here m is the total mass of the earth. And now, so long as the acceleration due to gravity g dash, that is at a depth d, is concerned, you should write g dash as g into m dash upon small r square. Now what is the meaning of this m dash? It has been proved by Newton that m dash is basically the mass of the earth of only so much radius. When you are at a depth d, the contribution of the outer mass is zero. It's only the inner mass of the earth. Inner mass means, if you imagine an earth of radius only small r, then whatever is its mass, that is the mass m dash here, and the distance also will be taken as only small r and not the capital R. You understand? M dash is basically mass of the earth of radius small r. And what is capital M? Capital M is mass of the earth of radius capital R. You understand? You can assume that the density of the earth is uniform. However, in reality it is not the case, but right now for all practical purposes we assume that the density is uniform. Then how will you express this m dash and m? You see, this capital M will be written as density of the earth into 4 by 3 pi r cube. But so long as this m dash is concerned, this will be density of the earth 4 pi by 3 small r cube. This is what we meant here. Rho is density of the earth. You understand? Rho is density of the earth. This has been assumed constant. This has been taken as constant. Now, if you see the ratio of these two, you can divide g dash by g, and if you substitute these two, this is g m dash by r square, this is capital G m by capital R square, and finally you will find that g dash by g is simply small r by capital R. This is the expression you will be getting. In case you want to replace this small r as capital R minus d, then you can also write it as g dash by g can be written as 1 minus small d by capital R. This is another way of writing the things. Here there is no special case. Whatever may be the depth d, you will find that acceleration due to gravity has same expression. This expression is telling you that acceleration due to gravity is varying linearly with small r. That means if you are at the center of the earth, then the acceleration due to gravity will be 0, and as you have started moving on the surface of the earth, towards the surface of the earth, then you will find that acceleration due to gravity has started increasing and it acquires maximum value on the surface of the earth, and the variation is linear. For example, on the surface of the earth, let us suppose the value is 10 meter per second square. Then if you are on the halfway, at half of the radius, then you will find the value is only 5 meter per second square. When you are at the center, then the acceleration due to gravity is 0. Now you have seen the variation due to altitude and due to depth. In case we try to correlate these two, try to see the graphical picture of these two, then it will look like this. Now essentially we are summarizing what is happening with depth and what is happening with altitude. For example, this was our earth. Consider that we are trying to plot the variation in acceleration due to gravity. This is the value g dash, you can say, and the distance we are counting from the center of the earth. This is a small r, and here we have plotted essentially the small r. This is the radius of the earth, capital R we are indicating. This is the center of the earth. We are trying to say that when you are on the surface of the earth, then the value of acceleration due to gravity is maximum. So maximum value may be this much, say 9.8 around, we have plotted here. As you are going above the surface of the earth, as you discussed in altitude, here you reach, the value has gone down. You go further, the value is further down. You go further, value is down. It is this kind of variation. The value is going down. You see, as you are moving on small r, the value of acceleration due to gravity is decreasing from 9.8, it will become 9, then 8, 7, like this, it will decrease. The variation, in case it is going down, and in case you plot it or join it by line, you will find it is following this kind of shape, and it should follow because you had derived that outside the surface of the earth, the acceleration due to gravity was following the rule 1 by r square, proportional to 1 by r square, inverse square law you can say. This is the situation when you are moving with altitude, it is going down. Now if you are moving inside due to depth, you have seen that the value decreases linearly. For example, here it is 10, then linearly it is going down, linearly. Linearly means you will find that the value is going down. Linearly means a straight line, because for a depth you had derived that acceleration due to gravity is proportional to small r. This is the picture of both the derivations which you have made, that due to depth it is varying linearly, decreasing linearly. At the center it is 0, you can see. On the surface it is maximum, and as you are going above the surface of the earth, whether this side or this side, the value is going down sharply, very fast it is going down, and it is proportional to 1 by r square. And same sort of graph will be on the other side also. If you see the variation, it will be symmetrical. The symmetrical kind of plot you can make this side as well. You understand? This side is r. Then you will find a similar kind of variation you will have here. As you will moving from the surface to the depth here, from the maximum value to 0, and if you are going above the surface of the earth this side, then also you will have this kind of variation. So this is the kind of picture you should keep in mind, that on the surface of the earth acceleration due to gravity is maximum. You are going above or going at a depth, the value of acceleration due to gravity will be decreasing. Now let us talk about the third factor which is responsible for the variation in acceleration due to gravity, and that is due to the rotation of the earth and latitude. For example, we are saying that on the surface of the value is maximum, but on the surface itself it is not same everywhere. On poles it is maximum, on equator it is minimum. So let us discuss the variation due to latitude and rotation of the earth. Let us discuss the third factor. due to latitude. Latitude is indicated by phi, and rotation of the earth. Rotational speed of the earth can be popularly indicated by omega. So for angular speed, the omega term which we are using, I am indicating by omega here. And now consider what is happening. Consider the earth, and you know that it is rotating at an angular speed, say omega. It takes almost 24 hours to rotate. So omega, for that matter, you can say 2 pi by 24 hours. And you see, latitude means, let's suppose you are here, you are somewhere here, then acceleration due to gravity will be pointing towards the center of the earth, and it should have a value g. In case the earth is not rotating, then you can say that the acceleration due to gravity is g, pointing towards the center. But in reality, what happens that when earth is rotating and you are on the surface of the earth, you can say a kind of centrifugal acceleration omega square r. Omega square r will also be acting on any particular mass which is kept on the surface of the earth. What is this small r? Small r is the distance of that point from the axis of rotation. If you are considering this to be the axis of rotation, then this small r is basically the distance from this axis, and that is shown here. Now you see, what is the concept of this latitude? Latitude is essentially the angle made by this radius with the equator. Here you should understand this is the equator, and whatever is your location, if you draw a radius here, whatever that radius at location will be making an angle with the horizontal, with the equator, that will be called the latitude phi. Now if the radius of the earth is capital R, that means this is capital R, the entire radius is capital R, then you can express this small r in terms of capital phi. You see, this angle will also be phi, and here you can imagine there is a right angle triangle where right angle is this, and you can say this small r is nothing but capital R, which is working as the hypotenuse, into cos phi. You understand? The small r which you have taken, this will be varying from place to place. If you are on the poles, the value of small r will be 0. If you are coming down up to equator, the value of small r will become maximum and equal to capital R itself. But on some other places of latitude, say 30 degree, 40 degree, the value will be different, expressed by capital R cos phi. Now you see, this omega square r, which is the additional acceleration acting outside, is due to the rotation of the earth. And on a particular latitude, say phi, if you look at the component of this omega square r, then you can say that this is the cos component of that, which is acting exactly opposite to this acceleration due to gravity, which is right now acting towards the center. So here you can say the component is omega square r cos phi. Understand? This omega square r is not acting exactly opposite to this acceleration due to gravity, rather it is acting at some angle. But in case you take the component of this omega r exactly opposite to this g, then that will be omega square r cos phi. For that matter, the net acceleration due to gravity, which you call g dash at this point, the net acceleration due to gravity g dash which is acting, it is equal to small g minus this omega square small r cos phi. You understand? Had the earth been not rotating, then this omega square r will not appear, and everywhere you will have the same value of acceleration due to gravity. But due to the rotation and latitude, this is the change, or you can say at different places the acceleration due to gravity becomes less. Now, if you substitute for small r as capital R cos phi, then you can write that g dash is g minus omega square. For small r you are replacing it by capital R cos phi, and there is another cos phi here, so this becomes square of that. This is the final expression you are getting. Understand? This is the final expression of acceleration due to gravity, in which the rotation of the earth omega is also taken into consideration, and the latitude phi is also taken into consideration. Now if you see the variation on the surface of the earth, then you can say at equator you can say phi is equal to 0 degree. You understand? On equator, if you are, this is equator, so on equator the value of phi will be 0. Now if you substitute this phi is equal to 0 here, then you will find that acceleration due to gravity is getting its minimum value, that is g minus omega square capital R. But if you are on poles, at poles, you have phi is equal to 90 degree. Why 90 degree? Because on poles means your position is here, and if you are going like that, phi value will become maximum, that is 90 degree. If you substitute 90 here, cos 90 becomes 0. So acceleration due to gravity g dash is equal to simply g. That is maximum on the poles and minimum on equator. This is the kind of variation you have on the surface of the earth. Now if you try to look at these expressions, what essentially they are trying to tell you is that if you are moving from one pole to another pole, first the acceleration due to gravity will decrease, it will become a minimum here, and if you keep moving, then on the other pole again from equator it starts increasing, and this becomes maximum on the other pole. This is the kind of variation you have. And in case somehow we give you some hypothetical question in which the rotational speed of the earth is varying somehow, then you see the value at poles will not be affected by the change in the rotational speed of the earth. But in case you are on other places, here or here, on equator or some latitude phi, then you will see that the rotational speed will make the effect. In case the rotational speed increases, then you will find that everywhere acceleration due to gravity will decrease. In case the omega decreases, the value of acceleration due to gravity will increase from its present value. We may ask you some hypothetical question that what can be the rotational speed or time period of rotation of the earth so that a body kept on equator feels weightless. That means they are essentially trying to concentrate on this equation and trying to tell you what should be the value of omega so that g dash becomes 0, or for that matter if you substitute omega is equal to 2 pi by t, then what should be the value of time period so that the body kept on equator becomes weightless. So all such calculations can be made with the help of these equations. Just for the sake of, you can say, remembering a data, you should understand that once the time period, if you look at that time period, that becomes 2 pi under root r by g, which is radius of the earth. When the time period becomes 2 pi under root r by g, if you calculate the value of this is approximately 84.6 minutes. Right now the time period of rotation of the earth is 24 hours, and in case it reduces to only 84.6 minutes, then you will find that anybody kept on equator will be feeling weightless. If you try to see the ratio means from present speed to the new speed, then you will find that new speed is almost 17 times its present value. That means 24 hours divided by 84.6 minutes, approximately it will give you 17 minutes. So these are some of the conceptual questions which will be asked, or maybe some numerical questions. Then you have to essentially use only these formulas of equator, that is G minus omega square R. So these were the three main factors involved for the variation of acceleration due to gravity. Now let us discuss some other concepts which are involved here. One more very important concept, that is called gravitational potential energy. Let us talk about that.